Welcome back, and in today's lesson we're going to cover the constitution of dry powders. Now typically this is going to take the form of one of two things. It's either going to be a powder that you add distilled water to make an oral suspension, such as an antibiotic for a child, or often many drug products that we give IV or IM start as a powder, and with the addition of sterile water for injection, normal saline, or other appropriate diluents, that powder then becomes a solution that can be injected. Now typically when pharmacists are reconstituting or constituting these powders, it's a pretty simple process because the manufacturer has instructions on exactly what to do. But sometimes there may be a range of solubility for a product that allows you to create different concentrations of the final product based on the amount of diluent added. And it's not always the case that the manufacturer's instructions will cover all of those options. Here's a case in point. This is the drug Rocephin or ceftriaxone, which is an intravenous or intramuscular antibiotic. And this comes straight from the product insert from the FDA website, where you can see that there are two different vials of powder for constitution that Rocephin comes in, a 500 milligram or a 1 gram. And if we look at either of them, you can see that there are instructions from the manufacturer on the amount of diluent to add to either create a 250 per mil or 350 per mil concentration. However, what if you wanted a 300 milligram per mil concentration? Well, the manufacturer doesn't give you instructions for that. And although it may seem like it would be simple, one thing you have to remember is that there's not a linear relationship between the amount of diluent added and the final concentration that results, and that's because the volume that the powder itself takes up within that vial is a stable thing. And because you lose that linear relationship, at times other calculations are needed. So when facing these calculations problems, you have to read the problem carefully to see if you're being asked to do anything different from the manufacturer's instructions or not. This is an example where you're not being asked to do anything special. It's just a very wordy problem that trips up a lot of students because of all the information that's given. But essentially, if you think about the process, and as you read through this on your own, you'll note that you're being told to add 300 units of penicillin G to a half-liter bag of D5W. And that portion itself, as you continue to read carefully, I'm going to strike out because this, other than the fact that we want 300,000 units, is really not that important otherwise. The other thing that's not really important in this is the fact that you add 1.6 mils of solvent to create a total solution of 2 mils. And that's because we're not being asked to do anything different from the manufacturer. Basically, if you get rid of all of the extra information in this problem, what we know is that we have a 1 million unit per 2 milliliter package of penicillin or vial of penicillin that you would have on hand as a pharmacist when you follow the instructions. So in order to solve this problem, it's simply saying, well, if I want 300,000 units and the vial I'm going to pull that out of is a 2 mil per 1 million unit vial, what do I need? And that's 0.6 mils. So the answer to this problem is, after you reconstitute the solution, you simply take out 0.6 milliliters, shoot it into your half-liter bag of D5W, and your drug is ready to go. But let's look at an example where we are trying to create a final concentration of product that's different from the manufacturer's instructions. And here's one here. We see that underlining in green, the manufacturer's instructions are you add 112 mils of water to a powder, and that results in a suspension of a final concentration of 250 per 5 of a total of 175 milliliters. So again, your volume, although you only add 112 milliliters of water, your final volume is 175 milliliters because there is a volume of powder contained within that antibiotic suspension. Now in this problem, we're actually being asked to make a different strength suspension, or a suspension that's 125 per 5. And the mistake I often see students make is say, well, if originally it was 250 per 5, and I want it to be 125 per 5, that's essentially diluted by half. I want it to be half strength. And so to do that, I just have to add double the amount of water. Yeah, no, that doesn't work that way. So let's go through how you do solve this problem. So anytime you have a powder for constitution where you're being asked to create a different concentration than manufacturer instructions, step one is figure out what is the volume of powder. And in this case, we figure that out by our manufacturer's instructions that our final product of 175 milliliters required 112 milliliters of water. And that means that 63 milliliters of volume must be from the powder. Now, no matter what we're going to do, that can't change. That's going to be stable. So that's step one. Step two is, well, what is our new total volume going to be based on the new concentration that we want? And if you haven't already reviewed the tutorial on altering product strength, you should go ahead and do that, because the way you do that is using our C1Q1 equals C2Q2 equation. So in this case, we know that if we follow the manufacturer's instructions, we get 175 mil of a 250 per 5 bottle. So that's our C1Q1. Now, what's going to be our new alteration? Well, we're solving for our new volume. I'm sorry, that's X milliliters of whatever we want, which is 125 per 5. So when we solve for X, we find out that the new total volume of this reconstituted product would be 350 milliliters. But again, that's the total volume. That's not the amount of water we add. We have to subtract the volume of the powder that we calculated above to figure out how much water to add. This means that we would actually add 287 milliliters of water. And so if you notice, this is not double 112. It's actually a bit more than that, exemplifying that nonlinear relationship. So let's look at one more example. In this case, we're back to penicillin G. We have a 1 million unit drug product. And we have the manufacturer's instructions, which I'm going to underline in blue, which is you reconstitute with 18 mils of sterile water for injection to get 50,000 units per mil. But we want to do something different. We only want 25,000 units per mil. So again, we want this to be a weaker concentration. So remember, step one is to figure out, well, what is the volume of powder in this package? Because that volume of powder that represents the 1 million units of drug can't change. Well, in this case, we don't have the total milliliters that the product is going to be after reconstitution, but we do know its final volume, which is right here in yellow, or the final concentration rather. So if you have a 1 million unit package and your final concentration after you make it according to manufacturer's instructions is a 50 million or 50,000 unit per mil concentration, then we know that the final volume would be 20 milliliters. But some of that was from the powder. How many milliliters of sterile water for injection did we have to add to get to that 20? Well, we added 18. So for our step one, if we minus the 18, we know that 2 mils is the volume of powder. Now we can go to step two, which is our C1Q1 equals C2Q2. So the concentration that the manufacturer calls for is a 50,000 unit per mil of a 20 milliliter vial. But the concentration we want is only 25,000 units per mil. And so we need to know how many milliliters is that going to be. So when you solve for X, X ends up being a new final concentration of 40 mils. So it is double. However, remember, it's only 2 mils is taken up by the powder. So we have to subtract 2 milliliters. And in this case, you would reconstitute with 38 milliliters of sterile water for injection. Again, if you simply doubled the 18, that would have only been 36, representing once again that nonlinear relationship. And that's why it's important to go ahead and do these problems carefully. So some tips for success is to read your problem carefully. If you're not doing anything different than what the manufacturer says to do, then just figure out what numbers you need to use. And sometimes it's helpful to think about the process of how you would make that product in order to figure out what the important data is. Once you've figured out the process you need to use, go ahead and solve your problem. So there are some examples of these problems in the calculations text as well as in some of the other resources that I've given to you. Go ahead and try them out, and if you're still confused, just drop me an email and we'll talk.